Hello everyone. For our little video lesson today, we're going to cover some basics of work and energy. Now, usually when I talk about work, I also introduce torque, even though we'll talk about torque later in this semester. It's because their formulas look very similar. Now, what we're primarily focused on is work, which is a form of energy. It is energy transferred during translational moment. That means an object that is moving in a straight line. And it could be positive or negative. However, that does not mean a vector like it would most other vectors, which are traveling in a Cartesian plane, left, right, up, down. That positive and negative sign could just mean whether energy is entering the system or if energy is leaving the system. Now, the units of work are going to be capital J or joules, and work is formally the dot product of force times the distance vector. Now, what that essentially means is we're trying to find the component of force that is parallel to our distance vector, or our displacement vector, I should say, which practically means that we'll take force times distance times the cosine of theta. When it comes to work, what we care about is some object that's being moved some distance d. And if force is not moving, if the force vector is not completely parallel with our displacement vector, then we want the angle between force and displacement. And that's the angle that we'll plug into here. And the combination of force times distance times cosine of theta, that is a scalar, or work. Which means that unlike with vectors, where we need to do vector components to add things together, once we get work values for our system's forces, we can add up all those works together. Now, that's not to get confused with torque. Torque is the analog of force during rotation, where force is moving something through translation in straight lines. Torque is moving something in rotation. It is actually a vector because we'll take force times the cross product of our distance rotation of our distance vector. Now, the cross product means that we're trying to get the part of force that is perpendicular to our distance, which also means that instead of cosine, we'll use sine. And a cross product of vectors gives us another vector. So force times distance times sine of theta gives us a new vector. And even though we still have force times distance, we are going to use for torque the units Newton meters. Even though in work a Newton times a meter gives us a joule, that is dealing with energy. When we're dealing with torque, we're using units of Newton meters. Now, because torque is a vector, we could have a negative torque or a positive torque that does mean some direction. If we have a force that is going to cause clockwise rotation, then we'll call that negative torque. And if we have a force that's going to cause counterclockwise rotation, then we'll assign that as positive torque. And torque here is represented by tau, and work here is represented by capital W. To explain the difference between work and torque, this top example was force and displacement for translational motion, and this was for work. Now, this is an example of rotational motion. So we're looking at torque. This X marks our point of rotation. So our bar can rotate like this, about this point. Our force is being applied at the corner here. So the distance between this force and our point of rotation is the X, or is the D right here. So we want this distance here between our point of rotation and wherever our force is. In other words, what we want is a y component to force, so we want the x distance away. And therefore, the angle between force and our distance vector That's the angle that we're using in our torque equation. Now for the remainder of this lesson, we're just going to focus on work. So let's say we have some 10 kilogram objects and we've already done the forces on that object. We're assuming acceleration due to gravity is 10. So 10 kilograms times 10 meters per second squared gets us 100 newtons. Force of gravity is straight down. And because our object is on a flat surface, the normal force is going to be straight up, perfectly canceling out our force of gravitation. So that will also be 100 newtons. We have an applied force, Fp, of 80 newtons to the right, and we have a force of friction, F sub f, of 30 newtons to the left. And as far as translational motion, this object is being displaced by a distance d of 5 meters to the right. Now, here's how we can look at the angles between our forces and our displacement vector. Our applied force is to the right and our displacement is to the right, so they're parallel and they're in the same direction. The angle that we would use here is 0 degrees. For both force of gravity and our normal force, F sub n, those are straight up and straight down for the normal force and gravity. Our distance vector is to the right, so straight up, straight down, that's 90 degrees, either way that we look at it, between those forces and our displacement. Now for our force of friction, it is to the left, but our displacement is to the right. If they're completely parallel, but they're pointed in opposite directions, use the angle 180 degrees instead. Now, let's say we want to calculate our net work, WNET, for our entire system. We have two ways to do it. The safe way, which is the long method, and then the net method, which is quicker, but you just need to be very comfortable with calculating your forces. Now let's look at the long method. We'll calculate work for every single force in our free body diagram. So our applied force would cause work P, WP, which is the applied force times the distance moved times cosine of the angle between them, or 0 degrees. The applied force is 80 newtons. The distance that was moved was 5 meters. And cosine of 0 degrees is just positive 1. That becomes positive 400 joules. Again, the positive and negative signs, they do not mean a vector when it comes to work. This is just whether energy is being applied or being removed from our system. Now in this case, Wn, the work of our normal force would be the normal force, F sub n, times distance, times cosine of the angle between those two, which is 90 degrees. Now cosine of 90 degrees, that is just 0. So anything times 0 gives us 0 joules. For the same reason, the work of gravity, Wg, is also going to equal 0 joules. Now we have the work of our force of friction, Wf. That equals our force of friction times our distance times cosine of the angle between them, which we're going to use 180 degrees. That comes out to 30 newtons for our force of friction, 5 newtons for or 5 meters for our distance, and then -1 for cosine of 180 degrees. So that all comes out to -150 joules. So because this is a scalar and not a vector, we don't need these works to be parallel. We can just add them all up together to get our net work. 400 plus 0 minus 150 gives us positive 250 joules of net work. Now what we notice is that work is working in translational motion. What we see here is that in the y direction, our force of gravity and our normal force cancel out. So there's no acceleration in the y direction, there's no movement in the y direction. Therefore, all we have for direction, translational motion, is along the x-axis. Therefore, our net work can be set equal to our net force times the distance moved times cosine of the angle between the two. Our net force in this case would be Fp, positive Fp because that's moving to the right, minus Ff, minus the force of friction. We're putting a minus sign here because that's pointing to the left. And then we'll multiply that by our distance d and cosine. And here's the reason why I'm using cosine of 0 degrees, because 80 newtons minus 30 newtons would be 50. We have more force pointed to the right, so our net force is going to be pointed to the right. Our displacement is pointed to the right, same direction, and they're parallel. That's going to be an angle 0. So Fp minus Ff, parentheses, times d times cosine of 0 degrees. That gets us 80 minus 30 newtons. And all that times 5 meters times positive 1, or positive 250 joules. So whether you use the long method or the net work method, the only thing that I've seen most errors happen is if you're using the net work method, be careful what angle you're using, because if we're given an angle here, if Fp is not parallel, Fnet would still be parallel. Now let's look at our work energy theorem. That is a theorem that says if you have calculated work, you have essentially calculated your change in kinetic energy. This is sort of like when we talked about impulse momentum theorem, or once you have impulse, you have the same magnitude as your change in momentum. However, unlike that situation, work and kinetic energy, they're both types of energy, which means we do not need to change the units whatsoever. Work is equal to the change in kinetic energy, delta Ke, or some textbooks might have delta K. Kinetic energy is equal to, well, the change in kinetic energy is 1/2 times the mass, m, times the change in velocity squared. That's change, parenthesis, v squared, parenthesis. In our words, 1/2 times mass, parenthesis, v final squared, minus v initial squared, parenthesis. A common error that I see in this subject is students taking the difference and then squaring it. Actually, you're squaring both velocities, and then you're taking the difference between them. Let's say we had an example where vi, or v initial, is positive 2 meters per second, and our displacement d is 20 meters to the right. And because we don't care about forces in our y direction right now, we have Fp of 16 newtons to the right, Ff of 5 newtons to the left, and we have a mass for our object of 5 kilograms. What would work be? Well, let's use our net work method of Fp minus Ff, 16 newtons minus 5 newtons. All that times our distance of 20 meters times our angle between the two. Remember that net force is going to be mostly going to the right. Our distance is going to the right, same direction, and they're parallel, so cosine of 0 degrees. This gives us our net work to be positive 220 joules. Now question 2, what would be the final velocity of this object? Well, rearranging our equation here, we already have the change in kinetic energy because that's the same value as our work. Now rearranging this equation here to get Vf, or velocity final, by itself, first we'll multiply to the other side. We'll multiply by 2 and then divide by mass. So kinetic energy, change in kinetic energy times 2 over m. Then we're going to take this minus vi squared and add it to the other side. So we have 2 delta Ke divided by m, all of that plus vi squared. That would be equal to vf squared, so then we'll square root both sides, so that the final velocity is the square root of 2 delta Ke divided by m, and then all that plus vi squared, but everything that I said is all under a square root sign. Therefore, our work came out to 220. We'll replace delta Ke with work. 220 joules times 2 divided by 5 kilograms. Whatever that equals, we'll add 2 meters per second squared. Joules divided by kilograms is a meter squared per second squared. Meter per second squared is still meters squared per second squared. Once we take the square root, that turns it back into meters per second, and that will also give us 9.6 meters per second as our final velocity. Now that's kinetic energy, or the energy of an object moving. Gravitational potential energy is a type of energy that an object has by being above a surface. We're going to use U, capital U, for potential energy, U subscript G for gravitational potential energy, and what we care about is the change in gravitational potential energy. That's going to equal mass, m, times gravitational acceleration, g, times delta h, or the change in height. For lecture, we're just going to assume that g equals 10 meters per second squared. And let's say we have a 25 kilogram object that is 5 meters above some surface. Well, in bringing that object up 5 meters, it has gained the following potential energy. There would be the mass, 25 kilograms, times the acceleration of gravity, 10 meters per second squared, times the change in height. Well, if it moved 5 meters, then that would be 5 meters. And if it moved up 5 meters, then we're using positive 5 meters. That comes out to positive 1,250 joules. Now let's say we have the example where we have a 10 kilogram object that's currently 6 meters above the surface, and we lift it higher to 14 meters above the surface. H1 equaling 6 meters, H2 equaling 14 meters. Well, the change in gravitational potential energy from this transition would be our mass, 10 kilograms for the object, times g, 10 meters per second squared, times the difference of height final, 14 meters, minus height initial, 6 meters. And that gives us positive 800 joules. Just like with work, energy is a scalar and not a vector. So these positive signs and or negative signs, they don't mean moving up or down or left or right, like with force or velocity or acceleration. It just means whether energy is being added to our system, going into our system, or if energy is leaving our system. And if you're an engineer, you might use a different direction, like negative for work out or positive for work in, but for physics, we're doing the opposite for right now. Now let's say we have spring potential energy. That would be represented with delta US, S being for spring. That's if you take a spring and you expand it or you compress it from its natural position. The change in spring potential energy is going to be 1/2 times K, which is our spring constant, times delta, parenthesis, x squared, parenthesis. X being our displacement from the natural position, or the natural length. Therefore, just like with kinetic energy, we're not squaring a difference, we're taking a difference of squares. So that delta, parenthesis, x squared, parenthesis, is x final squared minus x initial squared. Now, what we should have is xf is really L final minus Ln. L final means the final length of the spring, minus Ln, the natural length of the spring. That's not the natural log function, but just a way of saying the natural resting position of the spring. You might see L naught or L dot as well for natural length. That difference gets squared, and then we'll subtract another difference, which is length initial minus the natural length. L initial minus the natural length, that's what xi equals. LF minus the natural length. That's what XF equals. So in total, we have change in spring potential energy equals 1/2 times K times large parentheses, bracket LF minus LN, bracket squared, minus bracket Li minus Ln, bracket squared, large parentheses. In your actual calculators, you would just use parentheses instead of these brackets. That's just to help show you that we have something different inside these larger parentheses, just for the chalkboard. Now, let's say that we have a spring that its Ln or L naught is 2 meters. That's its resting position if it's not being stretched and not being compressed. And as far as our K value, the spring constant equals 1 kilogram per second squared. Let's say that that same spring is initially expanded to 4 meters, and that's what Li equals. And then in the final position, it's being expanded further to a new position of 6 meters, or LF. Therefore, our change in spring potential energy is going to be 1/2 times our spring constant, 1 kilogram per second squared, times large parentheses, 4 meters squared. This is because we have 6 meters minus 2 meters, or the final position minus the natural length. So that becomes 4 meters, and then we'll square that, minus 2 meters squared, parenthesis 2m parenthesis squared. That 2 comes from taking the initial length, 4, minus the natural length, 2. 4 minus 2, or 2. Therefore, 1/2 times 1 times the quantity of 4 squared minus 2 squared, parenthesis, gets us to 6. And a kilogram times a meter squared divided by second squared is just a capital J joule of energy. So positive 6 joules. Or we added more potential energy by expanding our spring even further past its resting position. Now let's say we have a totally different spring where its resting position is 10 meters. And in this particular case, the initial length happens to be the resting position. So Li, we're just going to say equals Ln in this case. Our spring constant is 2 kilograms per second squared. Let's do one example where we compress the spring from 10 meters down to its final length of 5 meters. And then a different example where we expand it from that resting position of 10 meters to 15 meters. Well, that's going to be done this way. For the compression example, we're going to have delta US equals 1/2 times 2 kilograms per second times the quantity of, now, we want to take the final position minus the resting length. So 5 meters minus 10 meters. And then we'll square that. And then we'll subtract that by the initial length minus the resting position. Well, in this case, the initial length equals the resting position. So that just becomes 0. 0 squared. Therefore, what we end up having is positive 25 joules of energy that we need to add to our spring to compress it by 5 meters. Now, in the expansion example, LF equals 15 meters, not 5. Now, that would mean that delta US equals 1/2 times 2 kilograms per second squared times the quantity LF minus Ln, which would be 15 meters minus the resting position of 10, and then that gets squared, minus, and then just like before, we have the initial length of 10 minus the resting position of 10 meters, and then we square that. So this still gives us positive 25 joules of energy. So when it comes to change in spring potential energy, if you compress it from its resting position by some distance, or if you expand it from its resting position by the same distance, you're going to have to add the same amount of energy in either situation. And now we're just going to look at a situation called mass spring systems, or you might hear them called spring mass systems. Essentially, we have a spring that's at its natural resting position. But let's say we add a 5 kilogram mass to the end of that spring, and after it's had some time to reach an equilibrium position, that equilibrium position is our change in height. That change in height is also our change in displacement. Now we're going to say that g equals 10 meters per second squared, and we're asked to find out what our spring constant k equals. Well, what we're going to first need to know is, at this equilibrium position, the restoring force of the spring, F sub s, that's trying to pull the spring back to its resting position, is completely canceled out by the force of gravity, the force that's keeping the mass pulled down. Now, because we just want the magnitudes of these two, we're going to say that Fs, the spring force, equals the spring constant times our change in displacement, k delta x. And here we have our force of gravity. That equals mass times acceleration of gravity, or mg. Now, setting those two equal to each other and solving for k, we'll get k equals mg over delta x. Now, we were told that the mass is 5 kilograms, acceleration of gravity is 10 meters per second squared, and we were told our change in height, which happens to also be our change in displacement of the spring, is 7 meters. That's because we're assuming that we were starting at the spring's natural resting position. Therefore, the change in height just equals the change in displacement. And that gives us 50 over 7 kilograms per second squared. So, just one more example for an advanced example of a mass spring system. Let's say that we initially have our spring in its resting position. It has an initial velocity of 0 meters per second and a mass of 16 kilograms. Its spring constant is the constant that we just found, so it's the same exact spring. The spring constant k is 50 kilograms over 7 seconds squared. G is still 10 meters per second squared. In our final position, we allow that 16 kilogram mass to pull the spring and allow it to eventually reach its resting position, or its new position, after being expanded. Well, that expansion is called delta x. And if we're going to find what that equals, well, then we're still going to set the restoring spring force equal to the force of gravity, which means that delta x is going to equal mg over k, or 16 kilograms times 10 meters per second squared, divided by the quantity 50 divided by 7 kilograms over second squared. That's going to give us 22.4 meters. And if you have a fraction here, make sure it's in parentheses so your calculator knows to divide the entire fraction correctly by order of operations. Now that's our change in displacement, 22.4 meters. Our object dropped a distance. That means it lost gravitational potential energy. We'll figure that out as delta UG equals mg delta h, which would be 16 kilograms for the mass, 10 meters per second squared for acceleration of gravity, and now our change in height, h, has the same magnitude as our change in displacement, but because our height involved a drop in change in height, instead of 22.4 meters, we're going to use negative 22.4 meters. And that comes out to delta UG equaling negative 3,584 joules. The third parameter that we can solve for is of the amount of energy that left the potential energy of our mass, how much potential energy went to the spring. Well, delta US equals 1/2 K times the change in parenthesis displacement squared parenthesis. That's 1/2 times 50 kilograms over 7 seconds squared times, and now our displacement here is 22.4 meters, and we're going to need to square that. That comes out to positive 1,792 joules. Now, for our change in kinetic energy, we had a lot of energy leave the mass, and we had some of that go into the spring. So we want to find out how much did not go to the spring, but instead went to the change in kinetic energy of our mass. Well, that's easy. Just take the absolute value of delta UG and then minus delta US. The reason being, this shows how much energy was lost by the mass for potential energy. We're going to change that positive because it might have gone to kinetic energy. But then we're going to subtract our answer from spring potential energy because that's how much did not leave UG to go to KE. And that ends up giving us delta KE equaling positive 1,792 joules because we had the absolute value of negative 3,584, absolute value sign minus 1,792 joules. Next thing we can solve for is our final velocity because we were given an initial velocity. Delta KE equals 1/2 mass times parenthesis V final squared minus V initial squared parenthesis. Therefore, what we end up getting is velocity final equaling the square root of VI squared plus 2 times the change in kinetic energy over mass. So we have 0 meters per second squared plus the term 2 times 1,792 joules divided by 16 kilograms. All that, those two terms added together and then taking the square root, that comes out to a final velocity of 4 square root of 14 meters per second, or approximately 15 meters per second. The next parameter that we could easily get is the amount of time that this transition took to go from here to first get to this position. Well, change in velocity equals the change in displacement over the change in time. So delta t equals delta x over delta v, and delta x over v final minus v initial. That would be 22.4 meters divided by 4 square root of 14 minus 0, or whatever actual value we were given for vi. That comes out to 1.4966 repeats seconds, which just for lecture, we're going to say roughly 1.5 seconds. A new concept that we're talking about is power, represented by capital P, and that equals joules divided by seconds. A joule over a second can just be replaced with capital W for watts. That's not the same W for work, but this instead means watts, or energy per time. So we use W 2 times, W as a symbol for work, W as a unit for watts of power. Now, funnily enough, power equals work over time. So this W does mean work. But because of our work energy theorem, we know that work can be replaced with a change in kinetic energy. So power equals the change in kinetic energy over time. If you needed it, work is still force times distance times cosine of theta, which distance over time, that's the same thing as velocity. So you do have a few equations for work, or for power, I should say. P equaling work over time, P equaling change in kinetic energy over time, P equaling F times D cosine theta divided by time, or power equaling force times velocity times cosine of theta, which is still the angle between our force vector and our velocity vector. Now, according to our system here, we can use we can figure out what power equals by using our work energy theorem to say that delta KE has the same value as what our work value was. Or work has the same value as kinetic energy change. So we're going to plug in 1,792 joules and divide by the time value we got, roughly 1.5 seconds, which gets us a power of 1,194.66 repeats watts, capital W, of power. And that concludes our lesson for work and energy and spring mass systems. Now, if you are not physically in my class, I'm still glad to have you all, and you're welcome to hit the like button, subscribe to the channel just to see that button turn into a rainbow for a second, and leave a comment. Or if you are in the class, you can do all that stuff too, or not. It really does not matter. But I'm glad to have you all here to hear this lesson. Wish you all the best, and as always, peace.